Good morning, good evening, good afternoon, wherever you are. Welcome to the public presentation of Technical Specification Connected Autonomous Vehicle. The acronym is MPAI-CAV technology, which is one part of this standard. Version 1.0. So first of all, why do we talk about connected and autonomous vehicles? Well, the first point is that, with this new types of vehicle, you can save life and you can reduce injuries because humans can have errors more frequently than machines. Not that machines are error-free, but certainly we can design and implement them so that they have much less errors. Then humans can have more time for better activity than just driving. We can optimize the use of vehicles in the infrastructure. So the CAV, the connected autonomous vehicle, can become an infrastructure, a transport infrastructure that is used when you need it. It can reduce congestion and pollutions. So the CAVs, instead of moving in the city to find a parking place, can move exactly for a purpose, and they can also better support elderly and disabled people. So the conclusion is that widely diffused connected autonomous vehicle will have a positive impact on society and individuals. So that's therefore we agree that CAVs are important, but the market is marginal, and therefore it will take a long time for the CAV market to make a difference, because today it is a marginal market. So in order to have a positive impact on society and individual, we must transform today's niche market into tomorrow's mass market. And it should be that quickly. So how can we do that? Well, we should just learn of what happened in the past. In the early 1900s, the cars were monolithic things. And, they were directed to a very rich market. Then gradually, things evolved towards the situation of today where the cars are made of components. Some components are made by the car manufacturer. Some are simply obtained from the open market. And now we have a mass market. Today, the CAVs are monolithic and they are directed to a luxury market. But we wanted to go towards a time when we have a mass market, and therefore CAVs should become component CAVs as much as component cars today. So how can we achieve that? We believe, and I believe, that the standards are a faster and more efficient route to achieve a market of interchangeable components than waiting for market forces to produce more and more monolithic cars that have higher SAE levels. So that is something that the situation of today, where we have standard components, not because they have been specified, but they have been the result of a long process. But if we wanted to accelerate and achieve the same result, we have to have standards that facilitate the definition of a component market. This is the name of the standard that I'm going to introduce today. And it has these features. A connected autonomous vehicle is partitioned into subsystems and components. The components have a functional requirements and they are identified. The format of the data exchanged by components are also specified. So this is what this partitioning means. So imagine that you are approaching your connected autonomous vehicle and you talk with a system that has been designed to talk with the humans. Then this system, if the humans say, take me home, has to contact another component that is called autonomous motion subsystem that can do that, but it has to know where it is, and therefore it requests another subsystem, which is the eyes and the ears of the CAV to tell it where it is. Then the environment sensing subsystem may also get additional information from the motion actuation subsystem. It provides a response. Therefore, the autonomous motion subsystem is able to tell the human CAV interaction what are the choices to go home. The human selects, and then when the car moves, it can get information from the environment. The environment is made by other connected autonomous vehicles or by other vehicles that are not necessarily CAV, but they have CAV capabilities. It can get from roadside units, or it can get even from people who are using their own handset. So this is the model that we are making reference to here. What kind of standard do we want to develop? So if we wanted to keep the promise of making specification that enable interoperability between components, but are not too constraining, we must adopt the interface standards. And interface standards have an interesting life cycle, where we have first we have the specification of what the system does. System can be the big thing or can be a small thing, and this is called functional requirements. Then the format of the data exchange through the interfaces. With this, it is important to remember that this does not mean that we freeze technological progress. Much of the opposite, we enable a competitive market where independent developers offer competing but interchangeable components that perform better and better over time. And this is the result of competition within the specification. Eventually, there will be an improved reference model that will replace the current reference model because it can no longer be exploited with another that is more powerful, and it can kick off a new sequence of performance improvement. So this is at the basis of the positive process that interface standards enable. What are the benefits? We can see that the researchers can work on optimizing component technologies. Component manufacturers bring their standard conforming components to market once they are mature. Car manufacturer, well, they have access to an open global market where they can find that the component that they need, and the components are interchangeable because the function is specified and the interfaces, but not the inside, is specified. Regulators have also helped because by making the system not a black box, but a component system, they have a better tools to oversee conformance testing of components using procedures that have been specified in the standard. And finally, I would say most importantly, users can have vehicles whose operation they can explain. I said that to some extent. Why do I say that? Well, because most of what we are talking about will be implemented with AI technologies, and you know all the issues that are about understanding exactly what an AI component does. What is important is that a CAV subsystem is not a black box. It could be designed as a black box, but then humans would have little knowledge and control of what a car is doing. And this is not a specific for the connected autonomous vehicle. MPAI has developed many other standards, and many of them use this enabling, this foundational standard that is called AI framework. The AI framework specifies a set of standard API that enable access to system functionalities. It supports systems, and the system is called workflow, AI workflow. Then we have components that are part of the workflow. They are called AI modules. And again, the AI module are specified by functional interfaces, not by how they are implemented, the technology that we use to implement them. And AI module instances can be replaced by AI module instances coming from a different manufacturer. Therefore, and this is a very important result for MPAI, that can be applied to this standard, we can have a specification that enables the development of components. So this is the AI framework I'm talking about. So this includes a workflow. We have 4 AI modules. Then we have storage that can be secure, non-secure. Then what is important is that we have APIs that are defined for communication, for storage, for access. Then we have security APIs. So this is a security abstraction layer that is very important for practical application, including the connected autonomous vehicle. So let's see then which are the subsystems that I've talked about. The first subsystem is called human-CAV interaction, the one that I have explained. So a human wants to go home and will ask the car, but in practice, it will ask the subsystem, which is human-CAV interaction, to do things. So, of course, what this subsystem must recognize the human, must respond to the human's command and queries, must also be able to have a conversation, must also be able to show itself as a perceptible entity, an avatar, a speaking avatar, should be able to exchange information with other subsystems, in particular the autonomous motion subsystem, the one that has the understanding of the route, but also is in control of the entire connected autonomous vehicle. And for instance, the passenger wants to stop. So the car is moving, but the passenger wants to stop or wants to see what the car is seeing, because of course the car is perceiving the environment, and that information may be made accessible to the human. And finally, the last functional requirement is that in the spirit of connected autonomous vehicle, this car should be able to communicate with the human-CAV interaction of other cars. So this is quite impressive. I agree with you, but I will try and explain how it works. Reference model for the human-CAV interaction. So here we have the audiovisual system description. It produces a description of what is around the car. Around the car, there may be speech. Maybe this is the speech of the user itself, him or herself. And this must be recognized, or it may be able to identify visual objects. All this goes into something that is called natural language understanding, that it refines the quality of the recognized speech, also extracts additional information called meaning. And then we also have the fact that the speech information is used to recognize the identity of the speaker. So if a human approaches the car and says, "Take me home," of course, the car wants to be sure that who is speaking is indeed the user or a rights holder. Same for the face. And then we have something that is technologically very challenging, but it is really the core of everything, is the entity dialogue processing. So it's something that receives a lot of information, which is the idea of the speaker, the description of the scene, the text that is uttered by the human. We have several other things, and it can provide an appropriate answer. One important point that is part of a specification developed by MPAI that is called multimodal conversation is personal status. So this is a representation of the internal status of a human. The human can be happy, can be sad, can be in a hurry. I mean, several things that are conveyed by a data format that has been specified by MPAI. So the car, the ACI, should be able to understand the personal status, and based on the personal status, the car should be able to define its own personal status with which the text that it pronounces should be expressed. And these are boxes that simply produce the output, the speech, of course, audio, of course, and then a visual, and the visual is here is the avatar representing the car. Something important that follows what I said about the ability for a human to see what the car sees is this audiovisual scene description here, and the human can request the car to provide this information that it can navigate at will. So let me move on. What is exactly part of the specification? For the subsystem, we have the input-output data, we have the functional requirement, and the function and the topology of the component that make the HCI subsystem. We have several input data that I have already seen, and we have several output data, again, that I have already shown before. This is rather detailed. I'm afraid I will not be able to give into detail, but this is just reported for the purpose of showing how thorough the specification is. So we define the input data, where they come from, what they are about, and in this links here, you can go to the web page where this point of view data type is specified. So I will give an example later of how the specification is done. So this for the input, this is for the output. Then we have the components. The components, for instance, I said that the audio-visual scene description. So it's the one that captures the audio and visual object from the appropriate devices and produces a descriptor of the audio-visual scene. We have automatic speech recognition, that's pretty clear. Visual object identification, yes, this is what gives an ID to a visual object. Natural language understanding is the component that refines the text produced by the automatic speech recognition. Then we have the speaker identity recognition. We have the personal status extraction. So this is exactly what I was saying before. The ability to understand the emotion that the user is carrying. And how is that expressed? Well, it can be expressed even from text. By reading a text, you can get an idea of what is the emotional state of the user, more from a speech, more from face, even from the gesture. So we have defined that these 4 entities all carry personal status information and what can be extracted, and there are ways to specify how this data are represented. So let me move on so these are the data type that come in and leave in an AI module. So for the audio visual scene description, of course, we have as input, we have audio and we have visual. And as output, well, of course, we have the descriptors. So the descriptors includes the objects in the scene and also their position and also their orientation. So that is what this AIM does. And the same can be done for the other AI modules. So let me look here at the data types that are required by this subsystem. So we have several. We have a 3D model. We have audio, of course. We have audiovisual scene descriptors. We have a message. So a message when an HCI sends a message to another HCI or receives a message from another HCI. Then we have orientation of the object, of an object. We have avatar. Portable avatar is a data type specified by MPAI, which is quite powerful because it contains more information than just the avatar itself. It can contain the speech, it can contain the text, it can contain information about the language, and so on. Now, this is another quite important element of the specification, which is not specific of the connected autonomous vehicle. Actually, it is something that is common to most MPAI standards. So what is a format? A format is how you represent a particular type of data. So you have a video. Video can have a format, but can also have another format. Formats are just the way you represent the same video. And this is done for 3D graphic, it's done for audio, for visual, but as we will see, there are many more other data types that can have a format. Now, a machine can understand data, can understand the video, but in order to do that, it must know how to interpret it. So it must know how to decode the format. Now, much battles in the market happen around formats. But here we are not interested in that kind of battles. We are interested in what video can provide, video as a data type. So the focus for MPAI, in particular for CAV, is on what kind of data type we are dealing with, not on the kind of format that is used to represent this data type. How do we manage that? We have defined a new specification that is called qualifier. And this qualifier conveys the information about the features of a data type. So we have the visual data type. You can say many things about the data type. Well, for instance, you can say, what is the color space that you are using for that data type? How was it encoded? How is it streamed? How is it described by metadata? I mean, all that information is conveyed by this qualifier because, I repeat, MPAI is not interested in fights about formats. It's interested in what a data type can do and how it can best be used in our standards. Okay, so this was the first subsystem. I now moved to the second one, which is the environment sensing subsystem. And this, as I said before, it is the eyes and ears of a CAV, but actually more than eyes and ears, as we will see in a second. So a CAV represents its environment using various specific environment sensing technologies. So we will see the list later, but we have audio and we have video, of course. But we also have LiDAR, and we have radar. We can have ultrasound. I mean, we have many more senses than the human, which only has eyes and ears. So how do we manage these different data types? Well, each data type is created by an environment sensing technology, radar, for instance. And so this is really the key point for this specification, is that all data type are represented with the same scene representation format. So we are not distinguishing between how a visual is represented. But we say, if it is visual, well, the scene should be represented in a certain way. And a radar scene, well, a radar scene includes objects. So therefore, we have to describe the object in the scene. We have to describe the objects, how they are positioned, oriented, and so on. So we have then a basic environment description, AIN, that integrates all this scene representation, and it produces the basic environment descriptor. So that is the best description of the environment that a car can produce by its own means. Then, a last point is that if there is a module that discovers a suspect object, suspect can be an object that one fraction of a second before was not present and now it is there. Of course, this is information that should be immediately sent to the brain that will process this information. So this is how the core element that I said, the scene representation format. So we have, say, as an example, the LiDAR scene description, it receives a LiDAR object, okay? We also know where this LiDAR object is placed. So we give it the spatial attitude. Spatial attitude means position, orientation, velocities, and accelerations of position and orientation. And then, this is important, we have available the information from other scene description that can be. So this is LiDAR, but maybe this car has also a camera, a visual camera. And therefore, the visual camera can benefit from the analysis that is made by the LiDAR and vice versa. And the output is the LiDAR scene descriptors, and if need be, an alert to be sent immediately to the brain. So this is the rather complex, but you know, it is very simple because each of these things here have the same model as before. This is just an integration of all this information, and this is alert information coming from each individual descriptors here, and sent to the autonomous motion subsystem that I like to call the brain. So these are the data types. I mean, we have several, we have point of view, we have, of course, a radar scene description. We have all the types of data types that are needed. So we have defined bounding box, for instance, the coordinates. Of course, we have the GPS is also part of the data types. Let me move to the next one, which is the autonomous motion subsystem. This is, as I said, it is really the brain because it receives from the environment sensing subsystem, the one that we have just seen, the basic environment descriptors. But we can do better because this is a connected autonomous vehicle. Therefore, if this module here has some doubts about the description of the environment, it can request remote cars to give the appropriate information. Then, of course, you can say, well, why should the other car decide to do that? Well, it's a reasonable question, but of course, if we wanted to have to benefit from each other understanding of the environment, this information may need to be protected in terms of privacy and so on and so on, but that information is vital and therefore should be made available. So then we have here the human CAV interaction, where the user is asking, take me home. So this information goes to this route selection planning, which finds among the many ways to reach the home, a few that may be proposed to the human. So the human selects, and based on that, the system decides to implement the route, and this is done in portions, and for each portion a trajectory is defined, and the trajectory is passed to this last AIM here, that this is the one receiving the alert that makes the final check if by any means this new information that arrived at the last second should not impact the trajectory that has been decided. If that is the case, a request is sent back to the motion selection planning. Give me another trajectory. Imagine if another trajectory is not available, then there is a request back to the path selection planning to give another path. In the disaster case that for some reason the road is blocked, maybe there is a need to request another route. All this information is stored here because the car may make use in the future of information that is being generated during this drive. Here are the data types. I will quickly move to that and just stay another second on this figure that says what I have said. This is the one receiving the route, selecting a path, passing it to the motion selection planning that decides the trajectory, and trajectory is given to the traffic obstacle avoider that just makes the last minute check that the trajectory is feasible. If not, a request is sent back. So this is an example of how the specification is made. This is part of the specification. We have this table. So every data type has a header. It is represented in a certain way, but I'm not going to spend time on it. Every data type has an ID. Then here is in the case when I am requesting you, and here I am giving you my ID, I am requesting you, how do you see this particular location? Because that is not clear to me, because maybe I have a truck in front of my eyes, the car's eyes, of course, and therefore, if I ask another car, maybe that car has the information that I need to have. Here is the response. Well, of course, there's the ID of the car that provides the response, and this is the piece of information that has been requested. Then, of course, as I said, around the spacing of IDs, there's a lot that can be said, but there are also ways to hide this information, but still make it available. So this is another case, more cases that, in the interest of time, I will skip. So this is just an example of how all the information is, all the data types have, say, the semantics table that I have just shown. The last, this is the part that actuates the message, move for the next 50 meters, and when you reach that point, you should have a velocity of 30 kilometers per hour, and and the car should have a rotation of 10 degrees, for instance, okay? So this is the message that is coming here. This message is interpreted here, it's converted into commands to brake, command to motor, and command to the wheel. So we are agnostic of what happens here, but we only specify what is the response that is provided. And this is all data types that are then analyzed here, and a response is provided to the brain or the car, which is, say, fully implemented, or for whatever reason, the instruction could not be fully implemented or not be implemented at all. And in that case, some other step, like I was showing before, a request of a new path and so on, may be needed. So let me come to a conclusion. What I like to say that this standard is a great example of the collaboration that we have inside the MPAI, because here we have different standards, and by different standard I mean different groups that have contributed technologies for the CAV-TEC specification. This is the AI framework I talked about. We need, of course, to be able to handle managed information. We need to handle objects and scenes. Yes, this is another standard. Sorry. Then we have, for the human CAV interaction, we need all the conversation technologies. Then we also need a technology to represent avatars. We need the technology to represent the environment. And you know, the good news is that we are sharing a technology with another standard that may look different, but it is not really so, because the metaverse, the MPAI metaverse model needs to represent the environment. In some cases, the environment is fully virtual, but in some other cases, the environment is a representation of a real environment. And then we have the last that concerns the qualifiers that I have talked about. So, I like to consider CAV-TEC version 1.0 as a stepping stone that allows us to move from the capabilities of a CAV in terms of interaction with humans, perception of the environment, creation of a model of the environment by collaboration with different CAVs, and move the CAV around to reach a destination. So this is what the CAV-TEC version 1.0 provides, but we should look to the future where the CAV becomes a full element of the Internet of Vehicles, interact with different services, and well, this is an ambitious plan to implement CAV-TEC version 1.0 as a running open source software. With that, I would like to look forward to working with you on this exciting MPAI project. cav.mpai.community is the link that you can use to access all the specification. And by the way, this is an opportunity to invite you to join MPAI and share the fun that we already have in building the future. Thank you.